I'd like to present the tactical blending solution from GEOVIA. Tactical blending is a solution that optimizes the additive materials for a industrial minerals operation, especially a cement quarry. I'm going to take a minute to describe the problem. So in a cement quarry, it's very common to purchase uh, third-party materials to supplement the material coming out of the quarry itself. The reason for this is they need to ensure that the material is of consistent quality when arriving to the mill or plant. And they use third-party materials to address shortcomings in the quality of the product coming out of the quarry. Now, the mining sequence really does determine what material comes out of the quarry, and that in turn determines the quantity and quality of the third-party materials required to make up for quality deficiencies. And several of the mining parameters can be adjusted, okay, so as to optimize the mining sequence within the quarry. So the problem then becomes this: which combination of mining parameters and third-party materials will provide an acceptable schedule with the minimum additive costs? That really is the problem that we are trying to solve. So let's have a look at the project in question. And it's quite simple. It's a single quarry sending um, a couple different materials to a few different places. The most important part here is that raw material goes to a raw product stockpile, but can also go directly to a plant. So the stockpile is used for blending purposes. Okay. So the issue with third-party materials is as follows. It is very common to have multiple suppliers of third-party materials. And every supplier is going to give um, a certain cost or price. It's also going to give a certain quality of material. Now, the quarry can pick and choose which material to purchase from which vendor. And they would pick and choose this according to whatever the shortcoming, quality shortcoming of the material coming out of the quarry is. So, for example, um, we can pick on in any given scheduling period um, material from an uh, aluminum material provider, silica, a mixed provider, or an iron provider. All of those are sort of necessary to supplement the material coming out of the quarry. But the issue is which is the best combination of these additive stockpiles. In this demonstration, there are up to 12 stockpiles, 3 for aluminum, 3 for silica, 3 for mix, and 3 for iron. So is this the best combination of stockpiles that helps me to address the quality shortcomings on a period by period basis of material coming out of the quarry? Or is this the best combination? Or is this? And not only that, but this combination, the optimum combination of additive stockpiles, in combination with the optimum combination of scheduling parameters such as mining direction, block size, um, mining rate, etc. So over and above the additive stockpiles, we have other scheduling parameters that we can adjust. We can have material ratio targets, so a target of the ratio of raw product to aggregates, as well as the ratio of raw product to cement. We have minimum and maximum additive draw rates from the additive stockpiles. Okay. And there are many other scheduling parameters that can be introduced as input factors for this solution. But how do we execute uh, um, the schedule and determine what is the optimum combination of the inputs. The way we do that is by using GEOVIA Mindshed, that is our tactical scheduling solution, in combination with Simulia Isight. Now, Isight is a software product used for simulation. It comes from our sister brand, Simulia. And what Isight does is it allows us to automate workflows or processes and to simulate that workflow across many different inputs. So Isight will allow us to automate just about any process or workflow, including those that contain tasks executed within Mindshed. Now, once we have Mindshed inside of Isight, we can ask Isight to loop that one scheduling scenario many times, hundreds of times, thousands of times. And Isight will orchestrate the execution of those many runs. Now, what it does when it's executing the same Mindshed scenario over and over again is it's varying all of the inputs that you choose. And the inputs could be which aluminum stockpile to use, which silica stockpile to use, which iron stockpile to use, mining rates, material ratio targets, quality targets, mining directions, precedences, lags, any of the scheduling parameters within Mindshed. As Isight executes the Mindshed scenario many times, it gathers all of the results and presents them to you in a results analysis window. So basically, the most important part here is that we can vary any number of inputs and track any number of outputs. And in the end, Isight will present them to you in a results analysis window for you to analyze, examine, and choose the best um, possible scenario. So practically speaking, in our simple cement quarry example, what it may look like is something like this. For the first execution, well, let's imagine we pick several hundred runs for this loop. In the first execution, it might use the first material ratio target might be 0.5, the second material ratio target might be 3.2, and the aluminum, silica, mix, and iron stockpiles, it may use the one of three. And we end up with an additive cost to the quarry of $212,000 for the life of the schedule. And what happens is Isight will simply run Mindshed again, except this time all the inputs are different. So it has different methodologies and techniques for how to vary the values of the inputs. So for the third run and the fourth run and the fifth run, you can see that there are different combination of the inputs. I haven't listed them all here. But an end result of the most important one being the additive cost. And one of these is optimum in the sense that we as users get to define what optimum means. And for this particular project, optimum is an acceptable schedule with the minimum additive cost. So in this slide, it would be run number 5. Now 5 is not is all I could fit on this screen, but uh, ideally you should run, it's easy to run an Isight model several hundred times, several thousand times. So in the end, what Isight presents to us in the results analysis window is something like the image I have on the screen here. In tabular form, every single run is a line, and the columns constitute all of the inputs and all of the outputs. The one in green is the one with a minimum additive cost. And Isight will not dictate that this one has to be the optimum. It is simply pointing out what is optimum according to your own defined optimization criteria. So the objective here obviously was to minimize the additive costs. The results after 17,000 runs was that we had a 76% reduction in additive costs over what a mining engineer was able to produce manually in Mineshed. I'll just take a minute now to show you the model in Isight and the results in the results analysis window. So this is Isight, and you can see the different nodes that are used to define the workflow. Here in these two nodes, we've got schedule, modify, and schedule run. So these are the two nodes in which Mineshed runs. First, we modify the scheduling scenario to tweak a production rate, to change the mining direction, to change the material ratio targets or the quality targets, etc. Once we schedule the run, uh, we calculate costs using a built-in calculator, and we track that information. So here I'm just going to tab over to the results, and you can see that there are a little over 17,000 runs. And if we scroll through them, you'll see some of them are marked blue. The blue ones have the same additive costs as the optimum one, so we've got lots of them here. 17,000 ones was quite a bit. And one of these, if I look for it, is in green. And that is the one with the not only the minimum additive costs, but uh, there were other optimizing factors here, including the material ratio targets. So this results analysis window is used to obviously review the results. We can filter out the results. We can even present them graphically. Even look at each of the inputs against each of the outputs. So it's actually creating some 2D scatter diagrams. And we can use these graphs, for example, to tell whether there is or is not any relationships between inputs and outputs. Very detailed graphical analysis. And that is it for tactical blending.